Ok, Ricardo.
Olá a todos, boa tarde. Hoje teremos mais uma palestra aqui na Escola Regional de Alto Desempenho do Centro-Oeste, né, evento organizado pela Faculdade de Computação, com suporte da Sociedade Brasileira de Computação e demais parceiros. Nós teremos agora a apresentação da Clarisse Taaffe-Hedglin. Ela é engenheira executiva. Ok, Mari?
Tudo ok, pode continuar.
Então, a Clarisse, que será a nossa apresentadora de hoje, ela é arquiteta de IT da IBM, tá? Ela vai nos apresentar, né, a palestra será em inglês, uma palestra sobre construindo um ambiente de computação de alto desempenho, dados, inteligência artificial e arquitetura de inteligência artificial em escala, tá? A palestra será em inglês, mas todos vocês podem fazer perguntas à vontade, tá? Tem os mediadores aí do chat no YouTube, e as perguntas de vocês podem ser em português, tá? Ou mesmo quem se tira à vontade pode fazer em inglês, serão depois levadas aqui para a apresentadora, tá bom? Fiquem bem à vontade, espero que aproveitem a palestra. Okay, Clarisse, I will introduce you first, right?
Okay.
And then you may start. So our presenter today is Clarisse Taaffe-Hedglin. So hope so I have said your name right. And yes. She's an executive IT architect at IBM. And so a short bio from Clarisse is she is, as I said, an executive IT architect in the IBM Garage for Systems with expertise on application performance and benchmarking. As a senior member of the Artificial Intelligence Center of Competency, she works with clients across many industries to shape their computer strategy, define architecture design, and prototype solutions in high-performance computing, analytics, machine learning, deep learning, to enhance insights from their data. Clarisse has many years' experience evaluating client data sets to tune systems, applications, and models for high performance and scalability, and her current focus is on bringing AI into the HPC workflow for increased productivity, and she also works with universities to bring in hand-on learning opportunities through labs and hackathons, and is an IBM Quantum Ambassador. She previously held a cross-platform technical management roles in IBM and started her career as a mainframe S319 vector facility developer. Clarisse has a background in numerical analysis and parallel systems optimization with a Master's of Science degree in mathematics from Purdue University. So, Clarisse, thank you very much for accepting our invitation. Thank you for being here with us today. And so, thank you again and welcome.
Thank you. Okay, and thank you, Ricardo, for that lengthy introduction. I apologize that I don't speak Portuguese, but I will try to be as clear as possible with my English and hopefully use more pictures than words, and it will be easy to follow. We're going to talk about what an HPC architecture looks like. This is more introductory, but most of the concepts that are important for a modern architecture for HPC and AI will be covered. So we'll talk about the compute elements, the network, and data and storage. Then we'll spend a little bit of time on programming models and what it means to have an integrated software stack, and conclude with some examples. This work is not just one team in IBM systems. Many components come into play with IBM, and I wanted to in particular point out the IBM research organization that includes a group in Brazil that that does a lot of fantastic work. So it's built upon years of IBM research and universities and partners to come up with these good HPC architectures. I work specifically with many universities in the United States to adopt these architectures, both for traditional HPC as well as artificial intelligence. And these are some of the partners that, that we have. So I will start with an analogy. When we talk about an HPC system, end to end, what we mean is all the pieces that have to come together. So instead of just an engine or fuel lines in a car, we look at the complete car, from engine to fuel to the drivetrain, and we build it all together so that there is a single point of contact to support and build these systems. So I may come back to this example often, but really the idea will be to talk about server, network, and storage together and how they all come together for a good solution, which is better than individual pieces. So at a very simple level, when we talk about HPC systems, we start usually thinking about compute nodes. So these are the engines that, that do the calculations on floating point operations. But an architecture includes much more than that. It needs to have data in the form of storage, so that's where your data resides. It needs a network so that you can communicate between the compute and the storage. And it needs a management system that includes login nodes, typically management servers that keep track of your images and your software licenses. And all these pieces come together through an administrative network in addition to a high-performance primary network. If you start at the very base, you have a core. This is the execution unit inside your processor that is doing the calculations. One or more cores combine into a processor, and then processor, memory, and network interfaces combine to make a node. So very often when we talk about HPC architectures and we want to size a system, we'll typically ask how many nodes the architecture is. Now those nodes can also have accelerators, caches, of course, and local disk. So that completes the single entity of the node. And then for high performance computing, parallelism becomes very important, and they are networked into these high performance systems. And that's the piece that then connects back to the storage as well. We've recently announced a new family to our power architecture. This is the architecture that has been used for the last decade or more to power our HPC clusters. And the most recent element of this family is a 7-nanometer Power 10 family. At each generation, the idea is to improve performance and energy consumption to get better and better performance and output from these chips. I won't go into specific details of each one, but this is a very base component to any HPC architecture. From those specific chips, then modules are typically built up from those. And that's how you build up multi-core systems beyond what each chip supports in terms of cores. This is also where you put your memory and you build up robust memory systems to go along with robust compute capabilities. And then finally, you can start scaling these out either within a single system, a single server, or across multiple servers with a high-speed network. One thing that is happening in the industry is you saw Power 10 is a 7-nanometer technology. There's a lot of challenges as we reduce the size of that over time. And the limits of, the physical limits of building faster and faster CPUs is approaching. Part of this is called Moore's Law, where doubling the number of transistors at regular intervals, typically every 18 months, is no longer a possibility. So that has slowed down. And what's happening is that the processor technology relative to price performance is not on the same path as it has been for the last decades. So there's a push in the industry to change some facets of the system architecture to come up with new things that take advantage of other ways to stay on that price performance curve. Those include improvements in operating system and firmware, the introduction of accelerators, which we'll talk about, as well as new algorithms and ways to leverage software, network, and storage to stay on that price performance curve that we've become accustomed to over the years. So that's one trend that's happening in modern HPC architectures. The other is the unlimited, it seems, growth in data, where for a very long time you just kept having more structured data, but at a predictable, maybe linear type of growth. And because of the advances in AI techniques and the availability of more and more data, especially unstructured data, such as images, you're getting more and more data that you need to be able to factor in and leverage to get better insights. We're also aware that data is truly a competitive advantage. And so building a system that's balanced between compute and that can take advantage of that data to get a competitive edge in your business or in your research makes a big difference. So these are some of the factors that are driving new and innovative HPC architectures. So I talked a little bit about acceleration. For us, in the past, it's mainly been GPUs, but there are two types of accelerators. There's GPUs and FPGAs. So GPUs are massively parallel processors that are doing floating point operations. They're working in conjunction together to get very, very high flops per second rates. And they work very well with traditional and emerging HPC algorithms where you can take advantage of that parallel nature of the compute that you're doing. They also require a rich ecosystem and specialized languages to think in terms of massively parallel computations. And so CUDA, which is NVIDIA's set of language and libraries, OpenACC, OpenCL are all examples of the ecosystem that you need to be able to take advantage of the GPUs. Field programmable gate arrays, FPGAs, tend to be more focused on very specific functions and repetitive functions that you need. So some of those examples might be with FFTs or compression engines that have a very specific role and are used to offload compute to take advantage of these specialized engines that accelerate your end results. And that tends to have a more limited set of languages and, in a sense, somewhat more complex to build. Now, the other factor relative to the compute piece is memory. And we typically talk about different memory models. The shared memory model has a common address space across all the cores and a shared memory bus. And it's cache coherent in terms of access. The challenge with a shared memory only model is that it's difficult to scale beyond lots of cores, and typically requires a single OS image. So this is what you'll see on a single server, typically. A distributed memory model takes that memory, has a local address space per node and a separate OS image per node. And there's explicit communication between the nodes through an interconnect to coordinate the memory. And that's called distributed memory, and you'll see that in HPC clusters. There's also the hybrid system where you have the combination of both, and that is very, very common with many codes, where you're having distributed memory across your cluster, as well as shared memory within your nodes. And you can take advantage of multiple threads to manage your workload and leverage that memory model. So we've talked a couple times already about how to connect the nodes in an HPC cluster. Most popular is InfiniBand today because of the higher speed that it offers, the lower latency, and it's basically the pervasive model for communications. And fat tree is typically the preferred network, although there are other types of networks such as Hypercube, Torus, and Dragonfly that have advantages as well. And the key here is that fat tree is pretty expensive because you're connecting many pieces, and so you can modify your network to take advantage of performance and cost metrics if those can help you reduce your primary network. We also see a fair amount of 100 gig Ethernet emerging, and also in artificial intelligence type workloads, we see a mix of InfiniBand and Ethernet. So there are different options with network that you can consider as your primary network. The other thing that we see as a trend is the idea of partitioned systems, partition clusters, where you've got islands and scalable units that build up your system, your architecture, and you have an InfiniBand at the core as your primary network, but you also have more localized networks within your island for faster computation. The last thing on networking that I wanted to mention is that in addition to your primary network, as you architect an HPC system, you do want to pay attention to your management networks, because you want to be able to have access and fast access to your storage, to your login nodes, to your cloud nodes, in addition to your pure compute nodes. So those tend to be Ethernet based and tend to have larger pipes, so that communications and data can travel quickly across your management network, in addition to the work that you're doing with I/O and compute on your application. I will take a quick break here and see if anybody had some questions on that overall architecture on the network and the compute pieces before I go into data.
All right, Clarisse. So for now, we don't have questions yet. So, but so one question I'd like to ask you is about, can you say something about how IBM is working with the network topologies in their HPC's products? Are they using InfiniBand or so FAT3 and?
Yes. So we primarily, our starting point is typically Mellanox InfiniBand as our partner, and we start with FAT3, and then we look to see from a workload perspective if that level of communication is required, or if there's potential for blocking and 2-to-1 or 3-to-1 type of blocking of the network. Otherwise, if we don't know too much, we start with the non-blocking FAT3 topology as our starting point. We've had some interest in Taurus and others, and you can see from the previous chart that, in fact, when we had our Blue Gene systems, it was a Taurus-based network. But for general purpose HPC and AI clusters, we tend to go with FAT3 as the starting point.
All right, thank you.
Okay, so let's keep going and focus on data as the next piece of our balanced architecture. And I won't go into HPC data too much, because that's fairly well known in terms of typically sequential data and using parallel file systems to access the data from a pretty much straightforward way. So I'll spend a little time to talk about what's new on the AI piece of this. And what's happening is that we're seeing data coming from so many different sources for AI pieces, and that can be transaction data, it could be sensor data, or data collected at the edge. It could be enterprise content from other systems, images, geospatial data, video data, sound data, social data, weather data, third-party purchase data. So there's a lot of different data sources, and they tend to reside in a lot of different places. So one of the things that we look at, even with the HPC architectures, is to start with understanding where your data is, where it's coming from, what kind of rates you need to be able to process that data, and then establishing a way to integrate and govern the data. So we'll spend a little bit more time on what that means and some of the pieces there. Some of the AI applications beyond using AI to accelerate HPC work with Bayesian optimization, for example, we're seeing a lot of applications relative to chatbots, personal assistants, optimizing supply chain quality inspection, dynamic pricing recommendation engines, looking at risk and fraud in the financial sector, insurance sector, leveraging the vision models from deep learning that have become so good over time to accelerate work using vision models, as well as behavior modeling, sentiment analysis, things that Watson, for example, can do very well with pre-built APIs. So the data pipeline, it's not just about having access to stored hot data to do your simulations or your AI modeling. It's really a data life cycle that starts from ingesting data, and you need to consider transient storage, how you're going to ingest data, and whether you've got fast real-time ingestion requirements. So this tends to be either lots of temporary landing storage that you may need, or it could be capacity or performance storage that you need depending on your ingestion of data rate. Then we go into organizing your data, and that requires some metadata analysis possibly, which we'll cover in the next chart, or traditional extract, transform, and load information, putting that data into lakes or large file systems, being able to access that data for your applications, doing some AI potentially on that data to increase your time decrease your time to results, and then finally archiving and saving that data if you need it. Most of this happens in a loop repeatedly. As you get more data, as you get more insights from your codes, or from your models, and you repeat and you start over with your data and being able to access all that data. And this is basically a high-level model of how you get from data to insights, whether it's through HPC applications or AI applications, and it applies to so many different use cases that almost every scenario can map how they're managing their data to an architecture that looks like this. So a little bit more on metadata, what that means. It's information that you have that is beyond your data that you're collecting. It's information about the type of data, the owner, the location, the permissions. It's about understanding what your data is with clues. The example here is biomedical data, where you could have some additional information on the different pieces of what that data includes. Images will give you some additional insights. You can apply AI to know what the image might be. Natural language processing as well. So it's a way to collect more information on your data before you even start your application, so that you know you've targeted the right information to feed into your applications. And so the focus on metadata, and in particular AI-derived metadata, is becoming more and more important in the overall architecture of your system, because the more you can do up front with your data, there's potential to get faster results for that as well. So we've talked a lot about faster time to science. This is going back and a little bit into introductory information on what makes a good HPC system. Traditionally, it's been about how fast you can do floating point arithmetic. And it's been typically double precision flops. In terms of the discussion of what peak flops are versus sustained flops. So the peak flops of a system are calculated as a function of how the CPU is architected and how the GPUs are architected in terms of how many cycles per core they can process, the system frequency, how fast the system is, versus and the number of cores. So peak flops is a calculation that is a theoretical maximum calculation of how many floating points you can do. In the real world, most workloads do not reach that peak calculation. And part of that is because it comes back to not just the processing, but also the I/O rates, the memory rates, and how efficient the codes can be to keep the floating point pipelines full to reach that maximum peak performance. The other trend that we've seen recently is that double precision still has its place for many, maybe even most workloads, but there are a number of workloads that don't need it and do better on single precision. And in fact, in the AI inference world, we're seeing even 16-bit and 8-bit arithmetic emerging with a lot of specialized floating point units to take advantage of those lesser precision requirements. The other two metrics that are useful in designing a system are memory bandwidth per floating point rate and network bandwidth per floating point rate. Excuse me. So some of the common benchmarks that are used for these are spec CPU. This has been available for many years and measures basically single server, single CPU integer and floating point performance. And there are two versions, base and peak, which allow different optimizations to get the most out of your architecture. Stream is the de facto industry standard for memory bandwidth, and LinPack is, HPL LinPack is the benchmark for measuring the compute piece of a supercomputer. And that can be measured from a single server all the way to a massively large supercomputer. Another emerging benchmark that's coming in from the AI piece is the ImageNet set of competitions. And these are image classifications algorithms. And in 2010, the error rate was about 28 to over 25%, meaning it missed classifying an image correctly for what it was 1 out of 4 times. And in 2012, there were new deep learning techniques that came about that have been improving year after year, where in 2017, the error in classifying images was 2.25%. And the reason this is significant is because the human error rate is somewhere between 7 and 4%. So we now have vision models that can do better than humans at detecting and predicting what class an image is, what you're looking at. So because of this, these algorithms have been able to be developed where you can use automated vision instead of human vision for things like quality inspection. And taking advantage of those techniques has greatly improved productivity. An example of that is on Summit, which was the top supercomputer in the world when it was announced, and it's showing different algorithms running on up to 384 GPUs. This is training of that model, and you can see the very large, nice linear scaling for the training, measured in seconds per epoch. An epoch is every time it iterates through the model, you time it. And it shows some performance improvements based on that. So this is very often a standard benchmark that is being asked to size a cluster, in particular a cluster of GPU-based systems. So when we talk about scalability, what does that mean? The definition that we use in IBM is it's the ability of a system or application to improve relative to adding additional resources and costs. So hardware scalability typically refers to cost, meaning you get the most out of your system based on how big you can grow your system. Software scalability typically talks about application scalability. Most applications have scaling limits within a system. So what that means is if you build a 4,000 node system, you may or may not get 4,000 nodes of productivity on that single application. So when you architect an HPC system, you want to factor in how well your applications scale and how much throughput you need, meaning how many concurrent applications you might be running. Those all coming to play to determine what the best architecture might be for your system. So when we talk about application scalability, there are two different types of scaling that you'll hear mentioned. So you'll see strong scaling, which is pretty common. That means the problem size is fixed, and as you add resources to that problem, you expect to reduce the amount of time it takes to solve that problem in some level of proportion to how many resources you add. So when you're looking at a performance chart, a constant improvement of performance as you increase resources is expected. If it flattens out, that means you're not gaining more performance by adding more resources. In weak scaling, you keep the problem size per processor fixed, meaning overall you grow your application size. And for that, you expect or you hope to keep your performance at a constant level as you add resources. And here, what you would like to see, or what you want to avoid seeing, is adding resources and seeing the time to solve your problem increase. An example of that is looking at an application that was doing quantum mechanics on Summit. It was run on 1,024 nodes. And there are a couple of things to note here. One is that the performance, so here lower is better, it's the time per step, decreases as you increase the number of nodes. That's a good thing. You also notice that the CPU performance is at one level of expectation, and that there's a large speed up as you have a well-tuned GPU version of this code, so you're getting a better GPU performance. And then you'll note that the performance was good up to 1,024 nodes, which is 20% of the largest supercomputer in the world, which is actually very impressive. Let me stop here and see if there are any questions on those concepts in terms of performance and how to understand and size HPC systems relative to price performance.
Oh, yeah. Clarisse, we have some questions. Let me read for you from the audience. Let's see. There is a question on the metadata that you show us in the slides before. How is the metadata gathered nowadays? Mostly are manual or from AI or another method?
Yes.
Can you say some words?
Yeah, so I think a lot of it is manual or built in, maybe from file names or how the data is organized. But there are tools that discover metadata for you. So in IBM, we have a tool called Spectrum Discover that helps build that data catalog by scanning basically the data that you have, and you can apply different tagging techniques, and some of it is still manual in the sense that you need to know what the data is to begin with, but there's better tools now to do some of that metadata organization more automatically.
All right, we have some other questions, but I think they'll be better asked you in the end of the presentation because they are from general topics, right?
Yep. Okay, so let's go into the last piece, which is some programming models and some examples and some of the trends that we see for that. So clearly, because of the requirement for a balanced system, and because of the explosion of data, the more you can bring the compute to the data and to the memory, the better it is. So we're seeing a trend to manage data in memory as a way to get access to that data quickly. We're also seeing the AI piece of this and taking advantage of AI to predict how to get results. So that's about identifying patterns and tuning parameters, for example, to leverage the patterns that are being identified by AI. It's also bringing in a higher level of abstraction in programming techniques. And then one thing that I haven't really talked about, but is pervasive through any architecture that you build in IT these days, and that is security, trust, and removal of bias in your models and how you manage your data. So for traditional parallel applications, message passing, and I heard in the previous talk, not that I understood too much, but I did hear MPI mentioned at least a few times as still one of the primary communication models. OpenMP takes advantage of that shared memory within and leverages parallelism within a server, and the CUDA piece, of course, for the GPU component. So the more tools you have to help automate all that, and really hybrid models seem to be favored where that's possible. Clearly taking advantage of multi-thread capabilities in your architecture is one way to drive these hybrid combinations. A lot of this still holds to the application programmer that really intimately know their code and are able to optimize to the architecture to take advantage of these programming models. I mentioned a little bit about having the right tools and libraries. The HPC specialists are always challenged between ease of use, where you can use built-in libraries and automated parallelism tools that are easy to implement and easy to support. And the extreme end on the other side is hand coding everything down to the GPU level, and that is more time intensive. But you can get better results than the automated tools that are available. So where you can leverage directives and libraries to get baseline good performance, that's sometimes sufficient, and where you need to optimize down to the most you can get out of your systems, you need to look at compiler, specialized compiler instructions, look at programming the GPUs directly, and so on. So that's always a trade-off between ease of use and best performance. Finally, when we talk about end-to-end pieces, we talked about the storage, we talked about MPI, compilers, leveraging AI, leveraging libraries. We should not forget about systems management, workload management, and some of the security and trust components of your solution. Workload management in particular, being able to have good tools to help with your scientist workflows, not just job submissions, but managing those job submissions and making the most out of the resources that you have available in your system, and being able to manage workflows and dependencies, and being able to monitor all that are critical components of your architecture. In IBM, we tend to leverage our collaborations with our clients, like the Summit supercomputer, as well as our open power contributions and open source contributions, so that it's a community effort. And we're doing that consistently. We just announced with open power, for example, that we were moving to a community-based support of the most popular open source deep learning frameworks like TensorFlow and PyTorch. So having all that end-to-end and being able to leverage an ecosystem that helps keep all these pieces together is another aspect of our architecture that we focus on. All right, so let's go through a couple quick examples and then conclude. So one very common example is building an HPC cluster for genome sequencing. This tends to be a smaller system, but not necessarily very small. And the challenge here is that it's about workflow. So you need automated tools that help you manage all the pieces, from data ingestion all the way to coming out with results and archiving that data. It's also very memory intensive and requires many petabytes of storage. So all the elements that I talked about are in there, in terms of interconnect, compute nodes, and parallel file systems, as well as the management piece to factor in the workflow and the data manipulations. So we've had some examples of this where we've put this together with our AC922, which is our Power 9 system to date, and our ESS spectrum scale systems, along with InfiniBand. And we've achieved 30 to 50 times faster end-to-end results with our whole genome and exome sequencing examples using GATK. The Summit system that I've given you already a few examples on is built on that same architectural concept with the compute racks, the InfiniBand switch, the high-speed storage, high-speed network. In addition to that, we had some flash disks to accelerate activities relative to getting the data fast and burst buffer support. And that system was a 200 petaflop system. And in fact, it's actually an exaops system if you look at AI operations inside the GPUs that were in the system. We're having many breakthroughs with Summit. Some of the work that has been happening on that supercomputer has been cancer research, high energy physics, fusion energy, and next generation material science. I won't go into too much detail here, but you will notice that it's not just traditional HPC, it's also AI algorithms that are coming into play for this groundbreaking research that's happening on that system. One example is that they were able to simulate 221 million atoms from the STMV industry use case, and got very, very good scaling results as a result of that. And you'll see HPC in the news all the time at this point. In early January, February, we announced that we were working with the US government and our partners, such as Oak Ridge, to establish a high-performance computing consortium that made resources available to COVID researchers, and a lot of good research has come out of that HPC work. And medical diagnostics is another example where AI and HPC are starting to intersect. This is a case of using vision models to differentiate normal X-rays to COVID-induced pneumonia images. So in summary, I'd like to reiterate that a modern HPC architecture doesn't just focus on flops. It balances compute, network, and data requirements. It takes advantage of accelerators and AI, with ultimately the goal being faster time to results. And the work we've done in IBM has been to really help accelerate the pieces of this type of architecture to get to results. And as you saw from some of the examples, HPC in general is impacting lives. So with that, I'll say thank you and see if there's any additional questions.
All right, Clarisse. So thank you for a very interesting presentation. So we have many questions here from the audience. Let me ask you some of them. Talking about AI, right? We have in the audience many students from the AI field, and so they are asking about, makes sense to have parallel AI algorithms. So the idea is, can you mention what's the benefits to parallelize an AI algorithm?
Yes. So one of the compute intensive pieces of AI is to train a model, meaning you iterate over and over, hoping that the system will learn from the input. That training is repetitive, and that it's very friendly to parallelism. So you can change your training time by adding more resources to the training. One of the best techniques for that is to use Horvath, for example, which is a library that breaks up your training into multiple servers. And so there's not a lot of work from a programming perspective that needs to be done to take advantage of that. And so the example I showed on Summit actually breaks apart the training for you by putting the computational piece across multiple servers. So there's been a lot of work relative to that distributed deep learning techniques. So that's one area. The other area relative to AI is using multiple servers with MPI, for example, under the covers. And that's also packaged and built so that there's not a lot of programming work to make that work. And that's been done, for example, for logistic regression with libraries such as SnapML, which basically spreads, it's the same concept, spreads it across multiple servers to accelerate your training.
Right, Clarisse, thank you. So I think your camera was turned off. So if you may turn it on if you want. It happens.
Let's see.
No worries.
And also the presentation, Ricardo.
Oh yeah. I think you stopped the sharing of your screen, so and went back to the last presentation. So if you stay your presentation shared.
Oh, it's lost in connection was detected. I guess I must have lost. Oh. So does anybody want to go back and see a chart? I don't know when it lost.
Okay, okay, Ricardo. Okay. The presentation and
they may go on, right?
Okay.
But I'm happy to share the presentation with anyone who...
Oh, that would be really, really nice. So I have other questions for you here. It's about applications on aviation. Do you have an experience or case studies to mention about HPC? So applications in the field of aviation using HPC?
No, the only thing I can think of is airplane design and fluid dynamic codes. So no, I don't have any specific use cases in aviation that I can think of.
All right, so we have questions here. Let me see. So it's about, we have a question here on programming languages targeting GPUs, right? So if you use a programming language targeting GPUs, you have more risk to use tools focus on scalability. If there's a complicated process to develop GPU applications, right? So I think the question is if you use so what's the impact of the program language on using applications focused on GPU, expecting to have better performance? I think the question is something like that.
Yeah. I think I understand. So the language itself may not have too much performance impact. Typically, we see things in Fortran, Python, and C++. One of the quicker ways for performance is being able to take advantage of libraries. And so depending on what kind of libraries and what kind of compiler acceleration and GPU acceleration you can take advantage of, that's one of the key things to look for.
All right. So more questions here. So we have some open questions now, and there's a question here about your expertise on quantum computing. So because in your short bio there is a mention on quantum computation. So the question is, how is quantum computation used in HPC process? If you can mention, I think you mentioned in the last slides, but if you can mention a little bit more about quantum computation on HPC projects.
Yes. So my official role relative to quantum in IBM is a quantum ambassador. That means I'm not part of the research team that's building and developing the quantum program. However, I've been trained to be able to talk about it and explain what it's about. And if you think about this, it's an emerging area of technology that will be used in a sense as an accelerator, just like we had other examples of accelerators. But the difference with quantum is that there's also the potential for completely new algorithms and a new paradigm shift, because every time you add a quantum, a qubit is the quantum entity that instead of bits, we talk about qubits, you double your solution space. So there's potential in HPC, and in particular, quantum chemistry, looking at energy fields, for example. There's potential to solve problems that are not solvable with classical computing. And so as these quantum systems get more robust and we can hold those quantum states longer, you're going to be able to potentially have breakthrough science as a result of these new and emerging quantum algorithms. So there's a lot of work going on in the research organization, looking at new algorithms, looking at how to build quantum systems that will give you that quantum advantage. So far they've been doing really an outstanding job, because they're doubling the capability of these quantum systems every year for the last few years. So there's a lot of potential, and certainly the field, the HPC field, where you can take advantage of a probabilistic or deterministic state with a lot of solutions in your solution space. There's really tremendous potential for quantum computing. So stay tuned. That's the next emerging area.
Oh, let's see. Hopefully. So we have so many other questions here, but we are now in our extra time. So I will just ask you one more questions. Maybe we can, you know, put together all the questions I left and send you if you have some time to answer that questions, you know, offline. And so the last question I'd like to ask you is from the students, undergraduate and graduate students. They are asking about the initiatives from IBM in order to popularize HPC and mostly the access to HPC infrastructure. And if you know something, or maybe Rodrigo, who is here, if you guys know some initiatives to help students or offer some infrastructure to you know, young researchers, undergraduate and graduate students to use HPC in their projects.
Yes. So actually, I'll start with the quantum piece because that's out on the cloud and available to anyone who wants to learn more about quantum. It's called the IBM Quantum Experience, and you can look it up on the web. Or I think the website. I'll have to look up the website and make sure that I can share it. But you can learn about quantum and quantum computation from there. For the HPC piece, probably the IBM developer, and there's some academic initiatives that are open that offer some options. And then any research work can get access to I think through applications to some of our supercomputers. I know that many universities have access to Summit for some research in addition to some of the other systems that are set up. So that tends to be more from academia to academia examples. And I know that University of Oregon has a program where they've opened up some resources to try out some of the IBM power systems for students.
So again, there are probably many more questions, and partly we don't have time for, you know, talking about all of them. But if you have time or in an offline time, we can put all together and send you, and you may answer the questions for the students. So, Clarisse, on behalf of the organizers of this event, I would like to thank you again for your time here, for having us, and for your very interesting and clear talk about the HPC topic. We have many students around Brazil, and mostly on your university. They are now working on HPC, and I'm sure they have, you know, enjoy your presentation too.
Well, I wish them luck and encourage them to stay in the field. It really is a fascinating, impactful field. So thank you.
Thank
Bye-bye.
you again, Clarisse. Bye-bye. See you. Acho que estamos finalizando